In this lecture, we will continue our discussion on the linked list class implementation. Let's take a look at the getNode methods, and we see there are two different versions of it. The first version lets us search for the node within the entire range of the list. So all we're doing here is we're calling getNode. The first argument is the index that we're trying to find, and then the next two arguments tell us the range. So we're going from 0 to size -1. The second method is the one where our search depends on where our index is. Here is the code for the second version of our getNode method. So we see that we pass the index, a lower bound, and an upper bound which specifies the range of where the index is. So we first create a reference variable of the node, so we can kind of go through our list here. We then check to make sure our index is within the lower and upper bounds. If not, then we're going to throw the index out of bounds exception. We're then going to check to see, is the index in the lower half of this range or in the upper half? So that's where we're doing this check. Like here, for example, we're checking if IDX is less than size divided by 2. If this is true, then we should search the lower half. So we use the begin marker as our starting point. And then we just follow up the list until we find our node. If it's not in the lower half, then it should be in the upper half. So that's where we have P being our end marker. And we're going to go in the opposite direction until we find the node we're looking for. So as I said, if the index is in that first half, then all we're going to do is we're just going to search the linked list starting at the front of the list. And if our index represents a node that's in the second half or the upper half of the list, then we'll start at that end of the list and work our way. That way we can cut down our search time a little bit. It's still going to take O of n time, but we can at least cut down the number of iterations. And as I mentioned before, we also have to make sure that our index is within the appropriate bounds. And if it isn't, then we're going to throw the index out of bounds exception. We'll next take a look at the linked list iterator class. And this has the same logic as the array list iterator class, except now we're dealing with linked lists instead of arrays. This one does involve a lot of error checking. And this is because, as we mentioned before, if we make changes to the list while the iterator is up, the iterator is no longer valid. So we need to be able to check for those types of errors. So the way this works is we have the current position, so the iterator will maintain that current position in our linked list. And here, current is going to represent the node where whenever we call next and it returns a node, it is that particular node. So what we're saying here is current is going to take a look at some node, and then whenever we call next, that is the node that current is currently looking at is what's going to be returned. Initially, it's going to be the node that comes immediately after the header node, assuming that the list is not empty, of course. But if there's something in there, it's initially going to be that first node in the list. That way, when we call next for the first time, it will give us the first node in the list. And then whenever current is actually positioned at end marker, if we try to call next again, it will be illegal, so we need to be able to handle that error. So now the question is, how do we know if there was a change made to the linked list structure after our iterator has been made? And this is where we use the expected mod count data field in our iterator. So this will initially be the value of mod count at the time that the iterator is created. As we do stuff with the iterator and the linked list, if we make a change to the linked list, that's going to change the value of mod count. So we can use this variable to see if there's been a change, because we can compare expected mod count with mod count. And if there was a change, that means we know that the values of these two variables have to be different. So if that happens, then we can throw the concurrent modification exception. We also have the OK to remove data field. So this is a Boolean variable that's true if we have called a next method without calling a subsequent remove. So this is initially false. So it's telling us that initially we're not okay to remove anything just yet. We have to call a next method before we can do a remove. So whenever we call next, we will set this variable to true. And then if we call the remove method, we would set this to false. And what this is saying is, if I remove a node from the linked list using the iterator, I cannot remove another node until I've called the next method again, because that way we can get the actual next iterator in our list, because otherwise our current iterator is kind of in this weird like purgatory state. In fact, if we try to call remove twice without calling a next, we will actually throw the illegal state exception. At least that's how we've implemented it in our code. So if we remove something, we have to call next again to make sure that it is okay to remove another node from the list. The hasNext method is fairly routine. So here's the code for it, and all it's really doing is just checking, is our iterator currently at the end marker? And if so, then this is going to return false, which means there isn't anything next. Otherwise, it's going to return true. The one thing that you should notice here is it does not check for any modifications of the linked list. So that may be something that's worth including in this method to before actually check to see if there's something else to see if there were any changes made to the linked list. The next method will give us the value of the current node that the iterator is looking at, and then we move on to the next iterator. So we change the value of current. So let's take a look at the code for that. So we do a couple checks first. We first check to see were there any changes made to the linked list, and if so, we're going to throw the concurrent modification exception, and then we're going to check to see is there something to go to? Is there a next node in our linked list? And if there isn't, then we're going to throw the no such element exception. Once we've done that, we will store the data of the current node. So we store that into next item, and then we change the value of current to the next node. And then notice that this is where we update the OK to remove. So we set that to true because now we've moved to the next node in our list, and then we return the value of the node that we were currently looking at before we moved over. The remove method is mostly error checking. So let's take a look at the code here to see what's going on. So we're first going to check the mod count and expected mod count variables to make sure they're the same. If they're different, then we need to throw the concurrent modification exception because they're different. It means that we have made changes to the list after we've created the iterator. We also need to check the OK to remove variable, because if it's not okay to remove anything and we're trying to remove, then we need to throw the illegal state exception. So we have to check that variable as well. So then we would actually remove the node in our linked list, and notice that we are using the linked list version. That's why we're using the mylinkedlist.this.remove instead of the iterator's remove method, because that would cause some problems. We talked about this before when we were talking about the iterator for the array list class. So here we're going to remove the specified node. So we're doing current.prev. We're passing that as the node we're going to remove. And notice that we have to increment expected mod count. And this is because in the remove method, it is incrementing mod count. So since it's incrementing mod count, we need to increment expected mod count because this removal is fine. We're okay to do this. And then finally, we are changing OK to remove to false because it's not okay to remove anything else. We've removed something, so we need to make sure that we get the next node for our iterator before we try to do another remove. So what we see here is the actual remove method mimics the same logic in the array list iterator class. And also what we find here is that current is going to remain unchanged because the node that current is, well, for lack of a better word, currently viewing is unaffected by the removal of the prior node because we're not removing the current node, we're removing the previous node. So that's what's going on here. We're removing the previous node. So that's why current is remaining unchanged.